The title of the talk has a bunch of terms, and over the last several years, I painfully learned that these words mean different things in different communities. So that was kind of a challenge to understand what they mean, and one of the punchlines of the talk will be that understanding more precisely what these words actually mean can lead to actual physical consequences, and there are many mistakes when confusions are present. So as a field theorist interested in condensed matter physics, I sought some kind of a dictionary between the notions in condensed matter physics and quantum field theory, and I should also add that there are some mathematicians interested in related topics, and their terminology is also different. And what makes it even more confusing that these dictionaries, I learned, are not one-to-one maps. So it's really getting very subtle. And sometimes even in the same paper, the same word means different things in different, I think in the same sentence they're consistent, but not beyond that. And I can actually pinpoint to papers. So in this endeavor of understanding the dictionary, many people have helped me, and among them many of the people here in the audience and other members of the collaboration. And absolutely this could not have been done without the Simons Foundation, which created that collaboration, which facilitated this interdisciplinary activity. I think this is what it's all about. But this is kind of very general. Two people were particularly helpful, and these are Monk Chang and Senti. And there were hours and hours of, I shouldn't say conversations, because with Senti, these are not conversations. But they have been enormously helpful. So the way I'm going to present that, the talk will have three parts. In part one, I will demonstrate all of these ideas in an utterly trivial system, in a system that everybody understands, system that is understood for more than a century, fully understood from many different points of view. And what I will do, I'll take this elementary trivial system and I'll present it in fancy language of more modern quantum field theory. And we will see gauging and anomalies, and there will be a 't Hooft anomaly and Adler-Bell-Jaquiev anomaly and all that, all in a very, very simple system. So one might say, this is an overkill. Why do we need the fancy language for a system that is fully understood, exactly solvable for about a century? And the reason is that once we will later be confused, both the terminology and how to think about these various notions, we can always go back to the trivial example and say, how did it work there? And as we go along, I'll show how the confusing terminology could be confusing in this particular system, and where nobody will get confused because the system is so simple. So this example will clarify this confusion and will lead us to the more complicated examples that we'll study later, and there will be many, many new results later, which from my perspective are possible only through the understanding of what is going on here. So what's this quantum mechanical system? It's a finite dimensional Hilbert space, k-dimensional Hilbert space, with vanishing Hamiltonian. It doesn't get much simpler than that. And if you want, you can even set k equals 2, but then most of the structure I will have cannot be seen. And it comes in the literature under various names. It's called the fuzzy torus, Glockenshift, Weil-Heisenberg algebra, particle on the torus in the lowest Landau level, and there are a dozen other terms for the same system. And we have a k-dimensional Hilbert space, and we're talking about two symmetries, two zk symmetries that act as clock and shift, depending on the way you like to represent them. And this is the algebra. These are the two zk's. But you see there's an interesting phase here. And what the phase tells us is that these two zk's do not commute. But the symmetry group is still zk times zk. This C number in between just tells us that the Hilbert space is in a projective representation of zk times zk. Now, I should emphasize this is not a new result. This is almost a century old. This is a paper by von Neumann and Wigner, who said that in classical physics, the symmetry acts linearly, but in quantum mechanics, the Hilbert space can be in a projective representation. So this phase reflects this projective representation. In modern terms, we would say that this projective phase is in a 't Hooft anomaly. And the 't Hooft anomaly is something that cannot be seen classically. It's really a property of the quantum system, of the symmetry in the quantum theory. And it's related to SPT in higher dimensions. Some people would say it's obstruction to gauging. And some people like to think about symmetries, whether it's on-site or not on-site, or whether it is on-sitable. This is on-site. I have only one site with a k-dimensional Hilbert space. This is on-site. The symmetry is there. I remember a very heated discussion with some people in the audience here in a castle in Germany, whether an anomaly means, I'm not going to mention names, whether an anomaly means that the theory is consistent or inconsistent, and whether we have to attach a bulk so that the theory with the anomaly really makes sense. This is it. You don't want any bulk here. This is just a k-dimensional Hilbert space. It has the anomaly. It's perfectly consistent. And if you think that condensed matter physicists are the only ones with misconceptions, when I grew up, an anomaly was related to the fact that there are fermions in the problem, and it's subtle to define the measure of the functional integral when there are fermions. No fermions or nothing. And also, the way it first appeared, there were divergences. You had to regularize the functional integral. There's nothing to regularize here. So we got rid of all these misconceptions, and now we can start discussing this system in more detail. So this is the algebra, and it has a zk symmetry, two of them, one for u and one for v, and I'm going to gauge a subgroup of it, the one generated by u to the m. So I'm taking k to be m times n, so I'm gauging this one. It's a Zn subgroup. And in the lowest Landau level problem, I'm taking the size of U, and I just reduce it by a factor of n, keeping the magnetic field the same, reducing the flux. So how do we do gauging? These are the two rules of gauging. Rule number one is called Gauss' law. I emphasize this should not be called confinement. Again, this is not confinement. This is Gauss' law. And at that point, you could ask, why does he even mention this trivial fact? It will be obvious soon. This is not confinement. This is just Gauss' law. And it has two manifestations. One is we restrict the operator to those that commute with the gauge transformation, u to the m. And we also restrict the Hilbert space to the subspace where u to the m is 1. So this is rule one. Rule two, again, old-fashioned gauging. We identify two operators. Since u to the m is 1, we are going to identify the operator O with O times u to the m. So let's see what happens to the two symmetries we had. The zk generated by V is explicitly broken to a subgroup. And if for zk of the u's, we have a quotient. So here we have a subgroup, and here we have a quotient. These are the hallmarks of gauging. We have a subgroup with respect to one group and a quotient with respect to another. And here it's kind of crystal clear that this is what's going on here. There could have been a typo. Where? The U. Ah, that's a typo. Thank you. Thank you. I'm very happy. At least one person pays attention. Right, yeah, this is a typo. I'll fix it for the next time. So let's track it in more detail. We no longer have V. We lost V because it's not gauge invariant. But we do have V tilde, which is V to the n. And therefore, the symmetry algebra, which had this at the beginning, at the end, we have that. And we say we have exactly the same system, except that K became M. So the Hilbert space got down by a factor of n. And let me say that in modern terms. In modern terms, we gauge an anomaly-free subgroup. This Zn did not have a phase with itself, did not have this projective phase. But this Zn had non-trivial phases with the elements in the other group, the group with V's. These anomalies, these phases with the other symmetry, the fact that we had a 't Hooft anomaly between this Zk and the other one, after we gauge, it becomes an Adler-Bell-Jaquiev anomaly, thus explicitly breaking the other one. So the explicit breaking of one of these Zks is a manifestation of what we call Adler-Bell-Jaquiev. Now, this is a very anachronistic way of saying it. This system was understood about 100 years ago, and Adler-Bell-Jaquiev was in the late 60s, and that's actually not what they did. But this is the modern way of seeing what's going on here, and we'll soon see generalizations of that. So you could ask, where are the gauge fields? I had operators acting on the Hilbert space. Where are the gauge fields here? Well, let me describe it in a way that exposes the gauge fields. So here is time, or Euclidean time, flowing along, and I need to project on u to the m equals 1. How do I project it? I insert various powers of u to the m along the time, and by summing over all of them, I perform a projection on u to the m equals 1. I have to sum over them with the right weight. This can be phrased as follows. This is my space-time, it's just time, it's a line. And when we have a gauge theory, we have to divide it into patches. And between two patches, we have transition functions. And we have u to the m is the transition function. So the sum over all possible insertions is exactly the same as the sum over the gauge fields. So we sum over the gauge fields by breaking it to all possible patches and sum over all possible transition functions. So the interpretation is that gauging that symmetry is the same as summing over all possible gauge fields. And these are described by these patches and transition functions, and these are this u to the m. So I just said in a very fancy modern way things that are fully understood in more elementary ways, because all of these ideas, and I put them here, every word here except the typo, were intentional, because every one of them will soon have a counterpart. Now, I'm going to do the same, a slightly different version of the same problem. Take the same system, and instead of projecting on u to the m equals 1, I'm going to deform the Hamiltonian by some arbitrary polynomial in u to the m. So the Hamiltonian was 0 before, and now it's a power series in u to the m. It's a polynomial, because there aren't that many powers that we can have. And we can bring it down in power series to from the exponent. And we get a picture which is very similar to the picture we had before. So instead of thinking of this as this is space-time with its patches and the transition functions, now these are operators that I brought down from the exponent. So this is very similar to the picture of the gauging, but the coefficients are now not exactly the same as the coefficients we had before. I emphasize it would be absurd, it would even be perverse to say that what we have is condensation of the operator u to the m. That's not what we have here. Whatever we have is not condensation of u to the m. U to the m yes, is some operator that exists here. No symmetry is spontaneously broken. We're in quantum mechanics with a k-dimensional Hilbert space. So nothing condenses here. So let's look at the Hilbert space in more detail. So we had k states. Now that we perturb by a polynomial by u to the m, the Hilbert space splits. And we have m states with u to the m equals 1, but then we have m states with u to the m with another phase, and m states with yet another phase. So let's see how this compares with the two gaugings, the two rules of gauging I had before. So for a generic polynomial, the ground state has this u to the m, and the other states have a higher energy. So what we did here was to impose Gauss' law energetically. So Gauss' law is not imposed as a projection operator, but instead we have a potential that the states that satisfy Gauss' law have low energy, and the other states are at higher energy. Yes? It's a mission. No, it's a mission. It's a polynomial such that it is a mission. It's a polynomial plus its dagger. But the dagger is u to the minus m. U is a unitary matrix. Yeah. Just let me finish this slide. So one line, you have seen that before, all of you. This is exactly what happens when we compare the toric code with Z2 gauge theory, where Gauss' law is imposed energetically. Yeah.
That have um equals 1 over those that have u to the m not equal to 1, would the polynomial be required to have positive coefficients, or?
No, the polynomial could be whatever you want, and as long as the coefficients are generic, there are no special degeneracies. And once you're done with that, I can always redefine u such that on the ground state u to the m is 1.
I see.
I think I even wrote it. Oh, I even wrote it here by redefining u. So we continue to do that. So let's compare that with the two rules of gauging. Rule number 1 was the explicit breaking. So what happens here, before, V was not gauge invariant. Now V does exist. It is a good operator, but it does not commute with the Hamiltonian. So that's how the symmetry was broken, because V exists, but it doesn't commute with the Hamiltonian. The second rule was the quotient. And we have a quotient because the full symmetry still acts. The full Z to the K still acts on the big Hilbert space. But on the ground state, only the quotient acts. Because on the ground state, the full symmetry is not realized faithfully. Only a quotient of it is realized faithfully on the ground state. This is, again, saying elementary things in fancier language, but that would be helpful. So we have a continuous deformation. I would say that the operator U to the M is proliferated, thus explicitly breaking a symmetry. So in my dictionary, when an operator proliferates, it explicitly breaks a symmetry. When an operator condenses, it spontaneously breaks a symmetry. You might or might not like this terminology, but this is the one I grew up with, so I'll stick with it. So there's no condensation here. Now, we can make the story a little bit more interesting, because so far, I picked an anomaly-free subgroup of U to the N, of ZK. I gauged it, and then I saw how I can do that in a continuous fashion via deformation. Now I'm going to do something more drastic, and I would do what one might call gauging an anomalous symmetry. This would, of course, be the wrong way to think about it. But I can take the same Hamiltonian, which was 0, and perturb it by a polynomial in V to the L and U to the M. So these two operators don't commute, which means that I cannot think of it as gauging any symmetry, because this is an anomalous symmetry that I'm trying to gauge. Instead, what I have is keep bringing them down. I have a picture like that, and two operators proliferate, both U to the M and V to the L. Now, of course, this is a very complicated way of saying something elementary. Take this system with K states, and write the Hamiltonian some polynomial in U to the M, V to the L. It's a K by K matrix, and you can diagonalize it. And it's totally unrelated to gauging because the symmetry is anomalous. Yet I can still think of it as proliferation. So what I proliferated is these operators that do not commute with each other, so the order matters more. But still, I can do it in perturbation theory. If I'm very powerful, I can even do it exactly. Now let me move to a slightly more sophisticated system. And I'm going to repeat all that with generalized global symmetries. So one slide review of generalized global symmetries. The standard symmetries are zero-form symmetries. The symmetry operator acts on codimension 1 in space-time. In the example before, space-time was one-dimensional, only time. And the symmetry operator was this U to the M. It acts at a point, which is codimension 1. And typically, the charged objects are particles. The one-form symmetry, denoted by this superscript 1 here, the symmetry operators act on codimension 1 in space. And typically, the charged objects are strings. And we can go to two-form symmetries, etc. So now we can turn the crank and do all the things we ordinarily do with ordinary symmetries and do them for these higher form symmetries. So we can have explicit or spontaneous symmetry breaking. We can use them to characterize phases. Is the higher form symmetry spontaneously broken or not? We have some kind of a generalized Landau paradigm. And we can have 't anomalies or SPTs and gauging, and then ABJ anomaly, etc. So whatever I did in the quantum mechanics can be generalized to zero-form symmetries in any dimensions, and now it can be generalized to any p-form symmetry in any dimensions. And more than 1,000 papers, I think, by now, analyzing this thing from various directions. So here is an example. Let's talk about TQFT in 2 + 1 dimensions. So from this point on till the end of the talk, I will be in 2 + 1 dimensions, even if I fail to mention that. So if this is a TQFT, the operators or the defects are lines, and they can braid. And the modern view is that every line in the TQFT generates a one-form symmetry. Some of them are invertible, some of them are non-invertible. For the purpose of this talk, we're going to focus only on invertible symmetries. And the non-trivial braiding between the different lines reflects in a 't anomaly of the one-form symmetry, or in the one-form symmetry. Very much like these U and V failing to commute in the quantum mechanics example. Here, this is the braiding in 2 + 1 dimensions. And if we have a global symmetry, we can gauge it. very much the same way we did it in the quantum mechanics example. Except using the phrase gauging a one-form symmetry, this is something that Greg and I did in '89. And we gauge what today we call gauging a one-form symmetry. The language there was it was a Chern-Simons theory, and we compared the Chern-Simons theory of the group with the Chern-Simons theory for the quotient of that group. And in modern terms, going from the group to the quotient of the group is the same as gauging a one-form symmetry. But for what it is, let's do it in pictures. What did we do for ordinary symmetries? The symmetry operator acts on surfaces in space-time. Got to act on all of space, but if we have space-time, they can act on surfaces. And gauging amounts to summing over all these surfaces. That's what I said earlier with the line. I have to sum over all these insertions of u to the m, because I have patches and transition functions, and I'm summing over the patches and the transition functions. So we could say that these surface operators proliferate, and that's what we did in quantum mechanics. Doing it for one-form symmetry is now straightforward. The symmetry operator is a line. So what we need to do is sum over all possible line insertions. And this picture was already mentioned in the '89 paper. And I apologize, we used the word condensation for the proliferation of these lines there. But actually, Greg Moore pointed it out to me earlier this week. Maybe I tried to repress this memory. So here it is. So this is a line that I'm interested in. It's fixed, and now I'm summing over the blue lines. So what would it mean? Gauging, I take whatever operators I have, whatever line configurations I have, and I sum over the insertions of the line, lines going in all possible directions. This is the same as performing the gauging. So we start with the bosonic TQFT. For simplicity, I'll be bosonic here. And I focus on an abelian enneon. Again, for simplicity, I'm only talking about abelian enneons. So the enneon has order n, which means that a to the n is 1. And now I find a new TQFT, denoted T over Zn, or T over the set generated by A, denoted the result after the gauging. Examples that you might know, Z10 going to Z5, U1 level 8 going to U1 level 2. And there are tons of examples. With increasing degree of complexity, we'll soon have more of them. So this can be done only when A is a boson, that we all know, which means that its spin is an integer. And that means that there are no self-braidings of A. And in modern terms, this means that there is no anomaly. The self-braiding of the enneon A is a manifestation of the anomaly. So we say that what we proliferate, this enneon should be a boson. Otherwise, the proliferation doesn't make sense. In terms of the gauging, this is the statement that there is no anomaly. So this is the summary. I'm going to proliferate these enneons and proliferate these enneon lines. And I emphasize that A, I proliferate rather than condense. And B, these are not the enneons that proliferate, but what I proliferate is the enneon word line, not the operator. There's no operator. What the operator is the line, and what I proliferate is the lines. I'm summing over insertions of the lines. So we had before the 2 rules of gauging. So now I have the 3 rules of gauging, because I'm in higher dimensions. So rule 1 is Gauss' law. So I remove all the lines that braid non-trivially with A. This is exactly the same as the rule 1 we had before for Gauss' law. And sometimes people call it confinement. So when I said that in the quantum mechanics, that it's perverse to call it confinement, it's equally perverse to call it confinement here, because nothing confines here. There's no area law in anything. The fact that the enneons that braid non-trivially with A are removed, that's not confinement. This is Gauss' law. And confinement is not the same as imposing gauge invariance. These are two different notions. Imposing gauge invariance is more elementary than confinement. You will get $1 million if you prove confinement. You're not going to get $1 million if you prove gauge invariance. And this proliferation also breaks a symmetry. All the lines that are removed can be thought of as broken. And that can be thought of as being an ABJ anomaly that started its life as the 't Hooft anomaly, the non-trivial braiding, but after the gauging, it turned into an ABJ anomaly. Rule 2, very much like in the quantum mechanics example, we identify 2 lines that differed by the gauge lines. This is the phenomenon of quotient that I mentioned earlier. So this was rule 2. And since we are in higher dimensions, we also have rule 3. If we have fixed points of the identification, so this configuration is not the same as that, and recall that I sum over all possible insertions of the blue line. So this needs special care. And then what it means is that this is analogous to people who know orbifolds where they are twisted sectors, or various other situations where you have twisted sectors. This is the same as the twisted sectors there, just 1 second. And that means that these lines appear multiple times. Confinement means that there is a line operator, typically the Wilson line, which exhibits area law in that phase. That's my definition. There's a well-defined order parameter which exhibits an area law. This is very similar to, in terms of the higher form symmetry, that what I just said is equal. There's an exact one-form symmetry, and it's not spontaneously broken. It's unbroken. If there is no one-form symmetry, there is no confinement. CEG, Fradkin-Schenker. Fradkin-Schenker is exactly the statement that the one-form symmetry is absent, and therefore there is no precise notion of confinement. Some people in the audience might not like that, but that's what Fradkin and Schenker said.
But there is a linear energetic cost.
For a while, and then it levels off. So for a while, there's a linear, and then it levels off. You have the same thing whenever you have a symmetry, it's ordinary symmetry that is not spontaneously broken. For a while, there might be, and then the correlation function goes to a constant. There's no symmetry. There's no precise order parameter.
So if I have a non-linear, that's also one.
Okay, that's a very interesting question. That's what people call a non-invertible symmetry. And what it means to gauge a non-invertible symmetry and to characterize anomalies in non-invertible symmetries, this is a topic that many people are working on today. Many people have very strong opinions on the subject. I'm not going to get into it. So for simplicity, I'm limiting myself to a billion anyons. So this is gauging a one-form symmetry. And because we had this rule 3, that some lines appear multiple times, we had a new dual symmetry. In the context of orbifolds, these are called quantum symmetries. And they're typically not faithful. And a subgroup of them acts on these lines. You see, it's always the red line. And depending on how many blue lines stick out of it, this might or might not be the same line, and this symmetry acts on it. So far, with the exception of using the words higher form symmetry, so with the exception of this terminology and some things I answered in questions, every single thing I said until now was 20th century physics. I started at the beginning of the 20th century, around the 20s, and then I talked about things in the 80s. So now it's time to move on. And we asked 3 questions. Can we follow the quantum mechanics example and find a phase transition for the proliferation? In other words, in quantum mechanics, we described first the gauging, and then we said we can turn on a parameter that pushes us from one phase to another. We can do the gauging in a continuous fashion by turning on an operator. Can we do the same thing here? Which, in terms of field theory, can we find a non-topological field theory that interpolates between one TQFT and another? Question number 2, in the quantum mechanics, I also showed a situation where I can proliferate operators that correspond to an anomalous symmetry. I had proliferate both U to the M and V to the L. So that's not something I can do with gauging. What's the counterpart of this here? By analogy, I should proliferate anyons that can braid non-trivially with each other. It's like gauging a symmetry which is anomalous. But I'm not gauging in a symmetry. Instead, I'm just going to proliferate it the same way I did it in the quantum mechanics. And since it was so easy in the quantum mechanics, nobody's going to stop me from doing it again here. And then this whole discussion should be generalized to non-invertible symmetry. Following your question, I'm not going to do it here today. Some people in the audience know a lot more about this than I. But this is something that I just mentioned here. So question number 1, can we follow the quantum mechanics example and find a phase transition associated with the proliferation? So we would like to have phase 1 with one TQFT, phase 2 with the other TQFT, and maybe some scalar field that couples to them and gets and takes us from one phase to another. So we're going to look for a non-topological UV theory that induces the transition. It has two phases, T and T prime. So this is the parameter space. We change a mass of a coefficient, mu square. Some say mass square of scalar field. And we have two phases. This is the original TQFT. This is the other one. And we would like to look for a field theory that describes this region of the transition. And through this conference, we have seen many speakers talking about exactly that. For example, Ashwin had a description of U1 level 2, and this side going to something else on the right-hand side. That's not quite gauging, but I will get to it soon. And Senthil earlier today also had some examples of that. And the literature is full of Chern-Simons Higgs theories that do this, exactly that. So naively, it's straightforward. We write a Chern-Simons description of this theory. We take a scalar field, phi, for the anion A, and then we just drive mu square negative, so the scalar field gets an expectation value. That's not quite precise, but it Higgses the group, and we find another TQFT. That's not so simple. So this topic has a long history, going back to a paper in 2009 by Bice and Singerland. And this author coined the name anion condensation, and as far as I can tell, they generated a huge confusion in the literature, partly by coining this term. And it took me a long time to convince some people that, yes, there is some confusion they created, and I'll explain it a little better, in what sense I think it's confusing. So first of all, I think it's better to refer to it as proliferation, because it's not the anion that condenses, if at all it proliferates, but it's not even the anion that proliferates, it's the anion line that proliferates. I'm summing over the lines, I'm not summing over the particle. Second, no symmetry, no global symmetry is spontaneously broken here. We have no global symmetry spontaneously broken, and in that sense, it's not condensation. If at all, we have explicit symmetry breaking, because as I said, through this ABJ, some symmetry is explicitly broken. Explicit symmetry breaking, in my terminology, is proliferation. In my terminology, the BKT transition is proliferation rather than condensation, because in the BKT transition, an operator that proliferates explicitly break a symmetry rather than spontaneously break a symmetry. So there's some dichotomy in the literature of two different things that are referred to as condensation. One, mostly in the math literature and in the more abstract part of UQM, we have a map between two different TQFTs. We have TQFT1, and the other one obtained by gauging a one-form symmetry. And people refer to it as I'm condensing an anion from this TQFT to that one. That's gauging a TQFT. I don't think it should be called condensation. And these things should really be distinguished from a proliferation transition, which describes a non-topological field theory, and we have a transition from phase 1 to phase 2. So people use the same phrase, sometimes even in the same paper, for two different things that they call anion condensation. Either a transition from one phase to another, or a map between two different TQFTs. There isn't necessarily a knob that takes me from one to the other. Yes?
Suppose you have a theory which is not Chern-Simons, so there are billion anion in there, but then you gauge it. Is that still apply?
It will still apply. In fact, I will soon give a general treatment. For the most general TQFT, a billion, non-a-billion, whatever.
Most TQFT have a billion anion, probably not Chern-Simons.
Oh, no, I mean, no. The whole theory can be non-abelian. I'm only proliferating in a billion anion in the big theory. It could be, for example, SU2 level 4, and that's non-abelian. It has an abelian anion. If I proliferate it, if I gauge it, I do not condense it. If I do that, it goes to SO3 level 4, which happens to be the same as SU3 level 1. I'm sure you know all these things better than I do. So that's a good example to keep in mind. And in fact, these people, over the years, I've talked to a lot of people, because from the paper, from 2008, I was going around saying, there's no condensation here, what are you talking about? And these people assured me, in different contexts, that over this period that there is actually an algorithm given T in an abelian enneon, which is anomaly free. There's a procedure to construct just a UV field theory that does the transition. Okay, so we'll discuss that soon. So that was question one. Question two, that at some point, hopefully it will be in 2026, there will be a paper on the subject with Mog. This question two was, okay, this is when the transition is an abelian enneon with zero anomaly, or in other words, this is an abelian enneon with integer spin. It can proliferate. What if the spin is not an integer? In the quantum mechanics, we had no problem. We had other proliferation transitions with u to the L and u to the m and v to the L. Can we have other transitions where the relevant enneon is not a boson? So this is the picture we have in mind. We have phase one T here, another phase here T prime, and a field theory that interpolates between them with a phase transition. And in fact, the example that Ashwin described earlier, was it yesterday, was exactly that. There was U1 level 2 here, and a trivial phase here. And some of the examples that Senthil described today also fall in this category. This is not the same proliferation that corresponds to gauging. It's another proliferation. So we would like to understand that better. So we are going to study all possible T's, possibly non-abelian, and they have an abelian enneon generating a one-form symmetry. And the anomaly is determined by an integer p. More precisely, it's labeled by an integer p modulo 2n. And for simplicity, I'm going to talk about bosonic theories rather than fermionic theories. So given T's, this is the data. We have a TQFT T and a choice of an abelian enneon A. The same answer I gave you before. The TQFT could be SU2 level 20. Since it's divisible by 4, there's a good abelian enneon. It's anomaly free. But now I'm much more liberal, and I say SU2 level 17. Level 17 has a one-form symmetry. That's right. It is a fermion. No, it is a fermion when it is 18, because it's not divisible by 4. I'm taking it odd. Okay. So it's even worse. SU2 level 17, it has a one-form symmetry. It's anomalous. Can we do this, something by proliferating it? Because as I said, we'd like to keep it as general as possible. So here are some examples with increasing degree of complexity. And every person in the audience can find exactly where, as we go down the list of complexity, where they would like to decouple. The first example is Z2 gauge theory, where I take A to be the E particle. Huge literature on this subject. Some of the authors of this literature are here in the audience. And this is one kind of transition we can discuss. Slightly more sophisticated one is U1 level K, where the enneon A is the one with charge M. M does not have to be a factor of K. And the order of the enneon is this, and the anomaly is given by some formula depending on K and M. That's slightly more involved. We can have a more general TQFT. It's labeled by a K matrix K, and the enneon is labeled by a Q vector Q. That's a more general one. And this data determines N and P. And this is the holy grail, the most general TQFT, possibly non-abelian, with the most general abelian enneon. And then we could probably generalize that to non-invertible symmetries, which I'm not going to do. So our goal is to find a field theory that describes this enneon. In other words, we sit deep in one phase. We have this TQFT T describing the low energy physics. And as we approach the phase, one particular enneon becomes light. In fact, if the enneon becomes light, all its powers also become light. And we would like to take a field theory that has that phase and ask ourselves, what can be there on the other side? So the field theory is not unique. The data I gave you so far is not unique. And there's an infinite number of Chern-Simons description of the same T. For example, I can always tensor in a decoupled TQFT, which is trivial. This abelian theory with 0, 1, 1, 0. So this is one thing I can couple in. But there are also many other groups. I mentioned in the question before, SO3 level 4 and SO3 level 4 and SU3 level 1 turn out to be the same. There are tons of examples. There's an infinite number of options. But even if we chose the gauge group and the anion, there are typically an infinite number of representations we can put the scalar field in. For example, in U1 level K, there are K first representations, but if we go to higher and higher charges, these representations repeat themselves. So we're going to get different answers depending on what we do. And also, A itself could be magnetic, so it would not even be a representation of the gauge group. I can say it in fancier way, but let's not do that. So we are going to look for a Chern-Simons description of them. And this is the data again. We have a choice of TQFT in an abelian anion A, and the spin of the anion determines P mod 2n. So we calculate that from these data. And then we would like to do the rest. And at this point, I'm going to make a simplifying assumption that the scalar field that I throw in is a single complex scalar field. That's the only assumption I'm going to make. So, and the question I'm going to pose now is, given this data, TQFT, choice of an abelian anion, and I'm allowing to have one complex scalar field for the transition rather than a multidimensional representation, what are the possible transitions? So it turns out that there's only one more piece of data that completely nails it down. It's this integer p, which appears here, but this determines it only mod 2n. So I think of it as an arbitrary integer p, and that turns out to be all there is. This is actually quite surprising, because first you think there would be only one answer, because one anions would be one answer. Then you realize that there are many, many possibilities, and if we have many possibilities, it looks like we opened a Pandora box, and there are lots of them. It turns out that the only freedom is in one integer. Yes?
So if you change this integer,
No. Well, in the theory with phi, the TQFT is exactly the same.
but there's always a TQFT can be associated with a conformal field.
That the conformal field theory is exactly the same. The conformal field theory is exactly the same. I'm now going beyond TQFT because I want to write a theory which is not topological, that includes the scalar field phi. So I'm asking, how should the scalar field phi couple to the TQFT? And there's an infinite number of ways it could do that, summarized by one integer, which is quite surprising. So here is a standard example. We take an abelian theory. This is the most general abelian theory. So we have a K matrix, and there's a Q vector. So there's an anion labeled by the Q vector Q, and we just say that the scalar field phi couples to the gauge fields according to these charges, and this is my theory. So that's easy to analyze. When mu square is positive, phi gets a mass, and we have the original TQFT. And if mu square is negative, phi gets an expectation value, sort of, and it Higgses the U1 to the R to a smaller subgroup, and that's the TQFT we find. So the puzzle we had before, there are infinitely many Ks, and for a given K, there's an infinite number of Qs which lead to the same anion. So the same TQFT is labeled by an infinite number of different Ks, not just by changing variables, because we can tensor different things and mix them, etc. And for a given K, there's an infinite number of Qs, because we can always shift Q by a vector of integers times K. So that gives us another Q. And they all look like it give us many different field theories, but these field theories differ only by the value of one integer, which is quite surprising. So what are the phases? When mu square is positive, as I said, these two terms are not important, and we have a gapped phase with K. And when mu square is negative, we have a gapped phase with T prime, and now I'm going to elaborate on that. So I'd like to give the general answer, what happens after the transition. So what did we do? We looked at this field theory. That is an exercise in field theory. That is where I feel comfortable. And it turns out that this field theory is quite subtle. It has a lot of interesting subtleties that I had to struggle with. And fortunately, I had Monk to help me with the subtleties. So first of all, the global symmetries. The coupling to phi breaks some of the one-form symmetry of the TQFT. So we have a smaller subgroup, we have a smaller one-form symmetry. And since A, the abelian anion A, might have self-braiding, the Zn one-form symmetry that is the hero of the story is explicitly broken to a subgroup. This is number 1. So there's some GCD of N and P. Much more surprising was a zero-form symmetry. This system has a U1 symmetry, which is actually extremely subtle. A subgroup of it acts faithfully on point operators, and the rest does not act on point operators, acts only on lines. This would take me too long to explain. This is actually extremely important to understand the other phase. And the theory has an operator, O, that carries charge under that U1 symmetry. It carries charge L under that larger symmetry. And also the local transition, the local dynamics near the transition depends only on the rational number P over N, which is again surprising, because we had an infinite number of theories labeled by all sorts of things. The local dynamics near the transition depends only on one rational number, P over N. In the case P equals 0 is particularly interesting, and I'll say more about it soon. And now you can take this whole story, use particle vortex duality, and have an equivalent version of the same story. Yes?
What determines the index L?
That's the details of the TQFT.
Okay.
There's an integer L that is determined by the details of the TQFT. But this is TQFT exercise. It does not depend on it does not depend on all the details of the non-topological part. So this is an exercise within the TQFT. And I emphasize that these symmetries, this and that, are present for any value of mu square. So they are true symmetries in the two phases. That's actually crucial for the consistency of the story. OK, so what do we have? When P is not 0, the mu square positive phase is gapped with the TQFT T. That was our starting point. So that's not a new result. But that's a new result. And it's somewhat surprising that the theory on the right-hand side, after the transition, this is what it is. It depends only on T and the choice of A and these integers N and P. This is a very close formula for the TQFT on the other side. So all the mess in the TQFT, it could be a very abstract TQFT. I didn't even tell you what it is kind of inert in this transition. So this is the final answer. And you can go and check various results in the literature, how there are special cases of this formula. But this is a universal formula. Yeah?
This is surprising that for the same interval, are many theories
The same?
What you just made the NEF redundant, and you kick it out.
Right. So
You kick out this particular.
that's the magic here. If you said, I'm trying to proliferate an anion,
So you're pretty all done by combine. So that,
I'm saying I approach and I see a TQFT, and there's an anion A. I'd like to proliferate it. In general, it's anomalous. I cannot even gauge it. So the answer is I tensor a particular thing that cancels the anomaly, and then I gauge it. That's the answer. You could ask me, how did I decide what to tensor?
that's my question.
And the answer is that it depends on one integer, P.
Okay.
Because P mod 2n is determined, and all these theories have the same anomaly, so this thing. But it is surprising that the answer is always the same. So all the complications of the TQFT, most of them are irrelevant here. So they determine the final answer, but all the freedom that you had is summarized by one integer. So this is a consistent quotient. That's a check. This is a sanity check, but this is the answer. For P equals 0, it's a little bit more interesting. This is the case which is anomaly-free. Notice when P is a multiple of 2n, it's also anomaly-free, but only P equals 0 is special. P equals 0 is special because for the first line, when mu square is positive, it's gapped with the TQFT T. But when mu square is negative, this operator O gets an expectation value and leads to spontaneous breaking of our global U1 symmetry that I talked so much about. We've actually seen that in the last talk. When Senthil described it in the last talk, he actually presented an example of exactly this phenomenon. There was a TQFT becoming gapless on the other side, right? It was gapless on the other side. This is a special case of our general formulas. And you see that when P equals 0, something funny happens here because the subscript here is 0. So we have a global U1 symmetry that I said earlier, it's quite interesting and subtle, and it is spontaneously broken on the other side of the transition. So the U1 symmetry is spontaneously broken, and then you can ask, what are we going to do about that? So option one is say, there's nothing sacred in the U1 global symmetry. Let's turn the operator O in the Lagrangian. Typically, it's a monopole operator. We can turn it on, explicitly break the symmetry, and then we have a TQFT on the right-hand side. And the TQFT is exactly that. So in this special case, the theory is anomaly-free, and we chose P to be exactly 0, then we have a transition from T to T prime, the transition that performs the quotient or the gauging. So this is the transition that implements the gauging. This is the proliferation transition. And surprisingly, a lot of the features of the theory on the other side, after the transition, are visible in the full UV theory. For example, I talked about some ZL part of the U1 symmetry. This is a symmetry that acts only on lines. And I said earlier that when you gauge, you go from T to T prime and you gauge, there could be a quantum symmetry or a dual symmetry that permutes the lines that split, that appeared several times. That symmetry is an exact symmetry of the full UV theory throughout the transition. This is very surprising because this symmetry is usually kind of very delicate. This brute force construction actually has that exact symmetry. And furthermore, this construction agrees with the construction of Mason, Mong, Pochen, Hotat, and perhaps others during these years. They were not as detailed as what we did here, but this thing agrees with what they did. And locally, but not globally, Senthil emphasized to us that this is actually a condensation transition, but only locally, but not globally. And we can spend another lunch or dinner arguing what condensation means, but I think with this sentence, I agree with that conclusion. That locally, but not globally, it is a condensation transition. But globally, it's not. Okay, one more comment I want to make. I can take this theory and try and enrich it. So I'll be very quick about that. I'm having in mind some UV system that has a U1 zero-form symmetry, for example, electromagnetism. And now we could like to enrich this whole story we had with that U1. And we ask, is this story compatible with studying not just the TQFT, but the enriched TQFT? And it turns out that the answer is no. So we have this U1 symmetry. I'll do it very quickly. The symmetry it should not be confused with the other zero-form symmetry I talked about earlier. And let us focus on this interesting case of P equals 0, where the transition performs the gauging. So without adding O, we had spontaneous breaking of the U1 symmetry, and we had a gapless phase. If we add O to the Lagrangian, we have explicit breaking. So if the U1 symmetry that we had at the beginning acts on this O, this is quite interesting, and it's different than what the TQFT answer is. Because if I enrich the system with U1A, the answer is that whenever the anion A has fractional charge under this enriching symmetry, then the TQFT answer is that one should extend this symmetry. I don't have time to get into a lot of details. And so this is the standard answer in TQFT, but that might not be compatible with the charge normalization in the UV. Alternatively, the operator O is charged under that symmetry, and then we had these two options. Either we turn it on in the Lagrangian and explicitly break the symmetry, and if not, the symmetry is spontaneously broken. And in this case, this happens to U1A. So again, in the example Senthil described earlier, there was a global U1 symmetry because it existed there microscopically, and his TQFT was enriched by that U1, and that U1 was spontaneously broken, leading to a superconductor. Now we see that this is a much more general result. This follows in any TQFT whenever P equals 0, and the anion has fractional charge under that U1, we have the same thing. But then we also have the option of turning on the symmetry, the operator, and explicitly breaking the symmetry. So the upshot of all that is in these cases, the transition field theory does do the gauging. So that's the good news. but that's incompatible with enrichment. So when people say, oh, gauging is the same as condensation, and I would liberally interpret that to mean as this proliferation. There is a field theory that does the proliferation. That's all very nice, but it's incompatible with enrichment. So even if I'm very liberal and I say, yeah, that's fine, you can call it whatever you want, that's not what you wanted. So here is how I finish. The talk had two parts. The first was background topics, kind of making sure that we are all on the same page with the terminology. We discussed global symmetry. We discussed 't Hooft anomalies, and in quantum mechanics, these projective representations. And then we said that gauging is possible only when the 't Hooft anomaly vanishes, and we demonstrated it in this simple quantum mechanics. And once we do that, the 't Hooft anomaly leads to explicit symmetry breaking, and that's a phenomenon of ABJ anomaly. And then we said that gauging can be thought of as proliferation of the symmetry operators. That's kind of obvious. We just sum over the transition functions. And this proliferation explicitly breaks the symmetry a la ABJ. So what's in gauging is the ABJ anomaly in the proliferation picture is just adding terms to the Hamiltonian. And we had similar discussion for higher form symmetries and their gauging. And then in the second half, I had new results. So we had a unified treatment of many phase transitions out of a general TQFT, T, including non-abelian ones. And it's very general that the TQFT, the details of the TQFT, very little of the details of the TQFT actually played any role. Associated with the proliferation of an abelian anion A that generates this one-form symmetry and its anomaly. And the transition field theory depends only on TA and one integer. That's kind of surprising. Out of the whole infinity of options, it's all lumped into one integer. And it has subtle symmetries that I mentioned. And for p not equal to 0, we have this simple formula for the result. TQFT for any p, that's the answer on the other face. So give me the anion, I know n. Give me t and the anion A, I know n. That's the order of the anion, and I know p mod 2n. Choose an integer p, and that's the TQFT on the other side. And it's really a lot of fun to go through a lot of examples in the literature and check how this general formula works. And it's non-trivial that it works. And for p equals 0, if I just follow my nose, we get a 0 here. And therefore, we end up with a gapless phase, whether we like it or not. And if we deform the model with an appropriate operator, in this case, it gaps the other side. And this is very similar to the gauging of the one-form symmetry. And the last result is that in some cases, this is incompatible with enrichment. So even if you like these transitions and you like enrichment, or you have to face enrichment because it exists in the system you're interested in, it's important to know that these two things are incompatible with each other. This is going to be now the last slide of this talk and of this conference, and in some sense of this collaboration, not quite. So I'd say thank you to everybody, including the Simons Foundation, especially the Simons Foundation. I think we should really thank them with applaud. They stimulated us. I learned a huge amount. This would not have happened without the Simons Foundation, so let's thank them.